Moving on to question 3 now, we have a question here dealing with proof by induction. So we've got a proof by mathematical induction that for n belonging to the naturals, that this summation here is equal to n over 2n plus 1. Okay, so 6 marks for this. So the best thing to do for any proof by induction question is to try and think about what you need at the end. So to figure out what I need for the end of this question, well, we're going to say let n be equal to k plus 1, right? That's always the last step of a proof by induction. So if n is equal to k plus 1, and if I sub that in here now, where my n's are, what will I get? Well, I'll get k plus 1 over 2 lots of k plus 1, so that's 2k plus 2, and then add an extra 1, so I get 2k plus 3. Okay, so this is what I need at the end. Okay, so that gives us a bit of an idea of what we should be ending up with. So now let's start the proof by induction. So the first case for any proof by induction is let n be equal to 1. I mean, you can let it be equal to a different value, but n equals 1 is always a very common one. So let n equals to 1. So what do I get on the left hand side? Well, left hand side, well, that's going to be equal to 1 over 2 lots of 1 minus 1. So it's going to be 1 over, so that bit will be 1. 2 lots of 1, so that's 2, plus an extra 1, that'll be 3. So it's 1 times 3. So that's equal to 1 over a third. Okay. So 1 over 3, a third. And then the right hand side, if we just do that over here, what will I get for the right hand side? Let n equal 1, so it's going to be 1 over 2 times 1, which is 2, plus an extra 1, so I'm going to get 1 over 3. Okay, so the right hand side is equal to the left hand side, so therefore true for n equals 1. Therefore, true for n equals 1. Okay, so that's the base case proved. Let's carry on now. So what we say next is that we're going to assume it's true for n equals k. So, assume true for n equals k. Okay, so if we assume this is true for n equals k, what would we end up with? Well, what we'd have is the summation going from r equals 1 to k, and it'd be this summation here, so it'd be 1 over 2r minus 1 times 2r plus 1, and this would be equal now, so if you put k in here, it'd be k over 2k plus 1. Okay, so just replace my n's with k, so it'd be k over 2k plus 1. Okay, so we're saying that's true, so this is true. Okay, so we've assumed it's true for n equals k. The next step now is to let n be equal to k plus 1. So let n be equal to k plus 1. Okay, and once we've subbed this n equals k plus 1 in, at some point once we've simplified, we should end up with this expression here, this k plus 1 over 2k plus 3. So I let n equal k plus 1, how can we work out this series, the summation? Well, let's rewrite the summation. So it's going from r is 1 up to k plus 1. Okay, well, remember for a series, so it's 2r minus 1, 2r plus 1. If I want the k plus 1 term, that would be the kth term plus the next one coming up. So the next term in the sequence after the k. So that'll be this term plus the next one. So if I write this down again, and we already know this is true, right? We've assumed it's true. So 2k plus 1. Well, my next term now will be this expression here, but with k plus 1 being subbed in for my r's. So let's write that down. So that'll be plus 1 over 2 lots of k plus 1, so that's 2k plus 2 minus 1, so I get 2k plus 1. Same here, but instead of it being 2k plus 1, it'll be 2k plus 3, because that's 2k plus 2 plus an extra 1. I get 2k plus 3. Okay, now what we need to try and do is get it over a common denominator, and this is nice and easy because that's a 2k plus 1, this has a 2k plus 1, so all I've got to do is times this bit here by 2k plus 3. So that gives me k lots of 2k plus 3 plus 1 all over 2k plus 1 times 2k plus 3. Now, what we can do is we can expand this. And notice now, we've got a 2k plus 3, that's what we need in the denominator. We've got a 2k plus 1 times 2k plus 3. So what we might expect here at some point is that the numerator will factorise, and then we can cancel terms. Okay, so let's keep expanding this numerator and simplifying. So k times 2k plus 3, so that'd be 2k squared plus 3k plus 1. And this is all over 2k plus 1 times 2k plus 3. Now we can try and factorise this numerator, which factorises quite nicely. So I do it all the way up here. So this 2k squared plus 3k plus 1, this will factorise, and this will give you 2k plus 1 times k plus 1. This is over, still the same denominator, so 2k plus 1 all over 2k plus 3. And this is perfect, right? Because now I can cancel my 2k plus 1 with that 2k plus 1, and all I get left with is k plus 1 over 2k plus 3. So therefore, this is equal to k plus 1 all over 2k plus 3. Perfect. That's exactly what we needed. So now, what we can say is that this general result, so general result is true for n equals k plus 1. K plus 1. And we've just got to finish with a little comment. So if I write the final comment up here, so as this is true for n equals 1, and we assumed it was true for n equals k, and true for n equals k, this implies, so this implies true, that is true for n equals k plus 1. So therefore, it's true for all n that belong to the naturals. So I'm not really good at doing this symbol, but there we go. So it's true for all n that belong to the naturals. So there we go. That's question 3, fully complete.